Hey guys, welcome to video 100. We're going to continue with our amplifier project, and today we're going to design the phase splitter, and we're going to make a few other modifications to what we've completed so far. So right now let's just review what we've got at this point. The design of the push-pull stage is essentially finished. All the currents and voltages that we designed for are shown over here. And we chose a Hammond 125E output transformer. Here it's wired up for an 8 ohm load. And I looked these up online and they're going for about $60 right now, which is not too bad. Now, based on some simplifying assumptions, the output stage parameters are VO max unclipped 13.4 volts peak, about 26 volts peak to peak. The maximum unclipped output power is about 10.2 watts RMS. We should have an overall voltage gain of the EL84s relative to the 8 ohm speaker of about 2.6. In reality, it'll probably be somewhat lower than that, but a gain greater than 1 for the push-pull stage is pretty good. And the input resistance is determined by the grid resistors we're using, which are 470 k ohms. What I want to do next is determine the input voltage at the grids of each of the EL84s that'll just drive the output into clipping. We do this by dividing the maximum unclipped output voltage by the gain of the push-pull stage. So 13.4 volts divided by 2.6 is 5.1 volts peak, or about 10 volts peak to peak on each grid. Now, because the push-pull section is so sensitive and we only need to get 10 volts peak to peak out of each of the outputs of the phase splitter, that makes the design of this section very simple. That'll be very easy for us to accomplish. So what I want to do now is choose a tube for the phase splitter. Basically, I can choose between the 12AX7, the 12AT7, or the 12AU7. And in this case, I'm going to go with the 12AU7. And the reason for that is based on the overall topology that we decided to go with here. If I use a 12AU7 here in the phase splitter, and say I use the second half here in stage 3, well, the phase splitter has about unity gain. This stage, if it's a 12AU7, might have a gain of 10, which isn't that high, but we have two other gain stages back here that I'll probably use a 12AX7 to implement. That means each of these stages could have a gain of around 50 or so, and that's more than enough gain to drive this amplifier into clipping, with just about any input or any tone stack that we'd use here. So we don't need to get astronomical gain from stage 3, so I'm not going to go with a 12AX7 here or a 12AT7. We're going to use the 12AU7 in this section, and that'll work out just fine. So let's go back to our schematic. We're going to use a 12AU7 here, and now let's go design that section of the circuit. Okay, you can see I cut the corner off of the 12AU7 plate curves and expanded it a bit to make it a little easier to see and also give us more room to work on the page. And I'm going to approach the design of this stage a little differently this time. What I'm going to do is start by drawing the DC load line that I'm after, and then we'll take a look at that and choose a suitable cue point. And looking at the circuit, one thing we know right from the beginning is that VPK cutoff is VPP, that's 275 volts. So one end point of our load line is going to be over here. And now we need to pick a suitable IP sat, and I'm going to go with 5 milliamps. That's a reasonable load line for this kind of amplifier. Now I'm going to fill in my VPK cutoff, 275 volts, and if we could move the cue point all the way to the left where IP sat is 5 milliamps, the midpoint of this load line would be about 138 volts, but we can't move that far. The cue point's going to stop when we hit VGK equals 0 volts, so that intersection looks like about 45 volts. So we're going to find the midpoint between 45 and 275, and that's 160 volts. So that is right here, 160, and that locates our cue point conveniently right about here at VGK equals -8 volts. And coming across to the left from the Q point, we see that IPQ is equal to 2 milliamps. Next, I want to come over and fill in some of these values over here. So we've got 2 milliamps IPQ. We're shooting for 160 volts from plate to cathode. And what I'm going to do then is split the rest of the supply voltage up between the drop on RP and the drop across RK1 and RK2. So that leaves me about 58 volts here and 58 volts total down here. But I need 8 volts dropped across RK1. So that leaves me 50 volts down across RK2. And now we can just use Ohm's law to find the value of these resistors. RP equals 58 volts divided by 2 milliamps. And that's 29 k ohms. Not a standard value, but I'm just going to use 27k. That'll be close enough. Down here, RK1 is 8 volts divided by 2 milliamps. RK1. 8 volts over 2 milliamps, and that gives us 4 k ohms. Closest standard value is 3.9 k ohms. That's good enough. And finally, RK2 is equal to 50 volts divided by 2 milliamps, which is 25 k ohms. And I could use either 22 or 27k, closest values there. I'm just going to go with 22k. And let's fill these in now. 27 k ohms, 3.9k, and 22k. And now we need to pick a value for R sub G. For the 12AU7, that could be as high as 1 megohm. But we'll play it conservative again, and we're going to go with 470 k ohms. And now, as you can see, I pasted in a much nicer version of this to save you from looking at my chicken scratch. And now let's go on over to the next page, and we're going to talk about the AC characteristics of this amplifier. Starting on the left-hand side, I've copied the circuit with the resistor values we determined placed in it, and I've also listed our design goals of IPQ of 2 milliamps, VPKQ 160 volts here, and I inserted the drops across these resistors based on 2 milliamps. Now, if you add them up, they don't quite come up to 275 volts. They actually add up to 265 because of rounding and so on, but they're close enough. Now, for convenience, we're going to assume the gain of the phase splitter is plus or minus 1. That is, each output has unity gain with respect to the input. In reality, it's going to be a little bit less than that, and we'll explore this a bit experimentally before things are finished here. But again, for convenience, we'll assume that the gain of this thing is plus or minus 1. Now, normally at this point we'd construct the AC load line, but in this case that's not really necessary because the load resistors are so large compared to the plate and cathode resistors. The AC load line is going to be virtually identical to the DC load line. And coming over to the right-hand side of the page, we've got the AC load line. Looking at it, it appears that we should be able to get an output swing of plus or minus 115 volts. I've called this V prime O max and V prime O min. But remember, when the plate is going negative, the cathode is going positive by the same amount, so they're going to meet roughly in the middle. So that effectively cuts the voltage swing in half for each of the outputs. We're splitting it evenly between the top and the bottom, and that gives us an actual VO max for either output of plus or minus 57 volts. Now, things are working out nice and symmetric here because I designed the circuit to have a Q point in the middle of its AC load line. If the Q point was not in the middle, then things would be asymmetrical and we'd have to do a little bit more work to figure things out. But fortunately, that's not the case here. Now, what we want to do next is determine whether or not the phase splitter is capable of driving the push-pull stage into clipping. Hopefully, you'll remember from the first page in the presentation that we need 5.2 volts peak at each grid of the EL84s to cause clipping on the output. Since the phase splitter is capable of delivering plus or minus 57 volts to the grids, it provides 10 times more drive than we need to cause clipping on the output, so we're in good shape here. And this brings us to another point we need to consider, and that is because the phase splitter can produce such large output voltages, it's possible that we could drive the grids of the EL84s positive with respect to their cathodes. And as we can see here, if Vin exceeds 10.5 volts, then the grid is more positive than the cathode, which is sitting at 10.5 volts, and we're going to get a large grid current. That's not a good thing. So what we're going to do here is add some grid stoppers to limit this current, and we'll talk about that in a little bit. But for right now, it's something that naturally comes into the discussion at this point, so I thought I'd mention it. Now, as you guys know, whenever possible, I like to build these circuits to demonstrate the theory we've been talking about, and this is no exception. So we're going to go on over to the next page and take a look at some measurements I made on this circuit. Okay, this is just a picture of the prototype circuit, and you can see I've got a transformer over here in the corner, and the reason that's in the circuit is to step up the output of my function generator. It's only capable of producing 20 volts peak to peak on its output, and I wanted more than that to drive this amplifier a bit harder, so I had to get creative, and that's why I put this step-up transformer in the circuit. Now if we go on over to the next page, these are the scope captures with an input of 10 volts peak to peak. The yellow waveform here is the output from the plate side. It's inverting, and it's 8.8 volts peak to peak, so the gain here is negative 0.88. The cathode output in blue is non-inverting, and it's got an amplitude of 8.4 volts peak to peak, so the gain there is 0.84. Now, if we were designing a high-fidelity amplifier, we'd want these two to match perfectly if possible. But in the case of a guitar amplifier, some mismatch here isn't going to hurt anything. And actually, these are pretty darn close, a lot closer than I thought they'd be. But now let's push the amplifier a little bit by increasing Vin and see what happens. Now I've cranked the input up to 80 volts peak to peak. This is the most I could get with my function generator and step-up transformer. And we can see the inverting output from the plate is 68 volts peak to peak. That's a voltage gain of negative 0.85, not much different than what we had before of negative 0.88. The non-inverting output from the cathode is 66 volts peak to peak, and the gain is almost the same as previously. It was 0.84, now it's 0.83. So we can see that the phase splitter is behaving very linearly with large changes in input voltage. Now, if I could have, I would have driven the phase splitter until it started clipping, but unfortunately I just didn't have that capability without messing around a lot more. And this is way more than we'd need to produce clipping on the output of the amplifier anyway. So the point of this whole thing is that our phase splitter is going to work just fine in this application. Now I want to address something I mentioned earlier, and that was grid stopper resistors. So let's go on over to the next page and we'll get into that topic. Here's the phase splitter with a simplified version of the push-pull output stage added, and I've inserted the grid stoppers here labeled R sub gamma. I used the subscript gamma because sometimes this is referred to as a gamma network because it looks like the Greek letter gamma, as we can see over here. I used 10k ohms for these resistors, and that's sufficient to limit the grid current to a safe value regardless of what happens over here at the phase splitter. Now, I should acknowledge at this point that I'm kind of treating the phase splitter like it was an ideal voltage amplifier and it's capable of sourcing any arbitrarily large current to a load, and that's not really the case. The most current we could get out of this would be about 10 milliamps, but that's still more than I'd like flowing into the grid under overdrive conditions. So adding the grid stoppers just gives us a little bit more insurance, and it decreases the maximum possible grid current even further. And there's a second benefit we get adding grid stoppers to the amplifier, and that is they form low-pass networks at the inputs of the EL84s, and this tends to reduce the sensitivity to RF noise pickup and oscillation, and that's what we're going to take a look at next. Okay, as far as the high frequency response of the amplifier goes, it's going to be limited to about 15 kilohertz by the output transformer, but the EL84s themselves have a response that extends up to 1 megahertz or so, and that's where the gamma network comes into play. If we disregard wiring and other construction related effects, all we have to deal with here at the input is derived from the parasitic capacitances associated with the EL84, and from the data sheet we've got a grid to plate capacitance of about 0.5 picofarads and a grid to everything else of about 10.8 picofarads. Now, looking into the grid of the EL84, these two capacitances appear in parallel, so they add together, except the grid to plate capacitance is in the feedback loop of an inverting amplifier, so it's going to be increased in value due to the Miller effect. We talked about that some back in video 55. In this case, the Miller effect causes the input capacitance from grid to plate to be increased by a factor of A prime V plus 1, where A prime V is the gain of the EL84. Now, we calculated that previously to be about 53, and if we plug the numbers into the formula here, we end up with a total input capacitance of about 37.5 picofarads. So the values for this low-pass network are R sub gamma is 10,000 ohms, Cin is 37.5 picofarads, and if we plug these values into the corner frequency equation for a first-order RC network, we get a corner frequency of about 424 kilohertz. Now, we could be a little more precise if we factored in the output resistance of this amplifier, but this is good enough. And if for whatever reason you wanted to decrease this frequency even further, all you need to do is increase the value of the grid stopper resistor over here. Now, there's one more thing I want to discuss before we wrap it up for today, so let's go on over to the next page, and we're going to talk about our coupling capacitors. The coupling capacitors we use determine the low frequency response of the amplifier because they form high pass networks at the output and input terminals. And for reference purposes, I put the plot of the asymptotic response for a first order high pass filter over here in the middle of the page. Ideally, the response is flat for all frequencies above f sub c, and it rolls off at 20 dB per decade for frequencies less than f sub c. Now, if we come back over to our circuit, notice that I used 0.1 microfarads for all coupling capacitors, and the reason I chose that value initially was because I knew it would guarantee that we'd have sufficient low frequency response. And it turns out if we calculate the corner frequency for these filters, it works out to be 3.4 hertz, and that's way lower than what we'd need. Even using drop D tuning, the lowest frequency we'd have to process is 73 hertz, so C2 and C3 are a lot larger than they need to be. Now, this extended low frequency response isn't necessarily bad, but it can result in a boomy sounding amplifier. And in the case of C2 and C3, where we're coupling to the output stage EL84s, we can get a kind of bad sounding distortion called blocking, and that's due to clamping occurring at the grids of the EL84s. To get a better idea of what clamping is and why it occurs, let's first think about how the amplifier operates under normal conditions when we're not overdriving the output tubes. In this situation, the grids of the EL84s are essentially open circuits. They look like infinite resistance, and the phase splitter is driving 470 k ohms, RL1, the entire time. Now, if we increase the output of the phase splitter enough, eventually we'll reach the point where the positive peaks forward bias the grids of the EL84s. When this occurs, we get a large grid current flowing, and the input resistance of the EL84s effectively drops from infinity to some low resistance value. The low resistance over here at the input of the EL84 causes our coupling capacitor to charge with this polarity, and then when the output of the phase splitter goes negative, the resistance over here is high again, and this negative charge on the capacitor amounts to a negative bias on the grid of the EL84, delaying its conduction the next half cycle and causing this blocking distortion. The same thing happens down here at the cathode output, but I'm just using this one for the sake of convenience. And you're probably saying to yourself now, okay, that's great, but what does the value of this capacitor have to do with anything? Well, the larger this cap is, the longer it takes to discharge and remove this effective bias on the grid. With this large resistor, 470 k ohms, that can take quite a while, so we're going to reduce the value of this capacitor to minimize the effects of blocking and hopefully eliminate it altogether for the most part. So if we decrease C2 and C3 by a factor of 10, make them 0.01 microfarads, that raises our corner frequency to 34 Hertz, which is still sufficient for anything we're going to need, and it's going to reduce the tendency for blocking to occur on the output. Now, the same principles can be applied at the input of the phase splitter as well. It's a little bit more complicated because we're not really looking at R sub G. Because that resistor is in the feedback loop of a non-inverting amplifier, the actual resistance we're going to look at is going to be much larger than that. So we can decrease C1 even further, but I'm just going to make it 1/10 of this value for convenience, and that'll work out just fine. So we're going to set all these capacitors to 0.01 microfarads. And this pretty much wraps up today's video, so we're going to go on over to the next page and take a look at what we've accomplished so far. We've got the push-pull section completed, and now we've added these grid stoppers, and we've reduced the value of these coupling capacitors to 0.01 microfarads. What we're going to do next is start looking at the driver stages back here, and once we get those designed, we'll pick values for our decoupling network here, R sub D and C sub D. But for today, that's all I've got, and I'll see you guys next time around.